Hi there, and welcome to the second in a series of GCSE forces videos or physics videos looking at forces. By the end, we will cover all of the course, but I thought forces would be a nice one to start off with. So this is the second one. The earlier video was looking at speed, velocity, and things like that, and distance time graphs and acceleration. This video is going to be looking at the types of force, vectors and scalars, resultant forces, and Hooke's law. So quite a lot to cover, so let's get started. So, force can be pushes, pulls, or sometimes they say twists. Can be cause an object to speed up, slow down, change direction, or change shape. Okay. Force is always measured in newtons, and to measure the force, you can use a Newton meter, as shown in that picture there. Okay. Hopefully, you've come across these things earlier down school before you came into GCSE. So, types of force. Then this is not totally including them all, but these are some of the main ones. Gravitational force, the attractive force exerted between bodies because of their mass. Now that force increases if either or both the masses are increased, and decreases if they're moved further apart. Weight is the gravitational force of the Earth on an object. Okay, and quite a lot of time students confuse weight and mass, which are quite different. Okay, so weight is measured in newtons, mass is measured in kilograms. Bathroom scales measure weight. A mass of 1 kilogram weighs about 10 newtons, roughly. Okay. Beyond the course, though, a stone is about 63 newtons, just out of interest. Then you've got the normal reaction or contact force. It's the repulsive force that stops two bodies moving into one another. The word normal means that the force acts 90 degrees to the surface of the bodies. It's caused by repulsive molecular forces, which you might find out if you do A-level physics. Okay. And there's an example there of a diagram of a funny looking car there with the weight and the normal reaction forces labeled there, okay, in a free body diagram for a stationary vehicle. Now, friction appears throughout physics examples, okay, and situations, and it opposes motion. The kinetic energy of an object, moving object, is converted to heat energy by the force of friction. Friction is needed for racing cars to grip the road, but it's also needed for walking there. Sadly, that person's fallen over because of lack of friction. Okay. Sometimes we get into our head that friction is always negative, but it is really useful. Okay, and allows us to do lots of things. So let's look at the negative effects. Okay, so you can reduce the negative effects of friction if you're trying to push objects by using wheels on a trolley, for example. You could use ball bearings in the example of the inline skates there, or you could use lubricants and polished surfaces so that they're smooth, and that will reduce the effect of friction. You could use an air cushion, like on a linear air track that you might have seen in the classroom, for example, or on that maglev train there, okay? But you can sometimes want to enhance the effects of friction, the positive effects. So having good tread on a tire, for example, okay? Using a parachute if you're free falling, and using chalk, that kind of thing, for rock climbers, okay, to increase the friction so they don't slip in the hand grip. Now, one thing that comes up a lot, certainly in the next video when we look at terminal velocity, is air resistance or drag. So that's the force that opposes the movement of objects through air. Drag is a more general term, and I think I've changed my teaching over the years to try and use the word drag more often as opposed to air resistance, because the word drag can be applied if the object's moving in a gas or a liquid, so any fluid, okay, fluid being a gas or a liquid. So I know that the last couple of years, some of my students have struggled with exam questions on liquids, where something's falling through water, and they're trying to describe this opposing force. And so they might say water resistance or something like that, which isn't always accepted. Okay, but drag is a more universal term. Okay, so that's a bit of exam technique there. Objects are often streamlined to reduce that force, although not in the case of the parachute, but maybe in the case of that car. Upthrust is something that doesn't come up that often, I don't think, anymore in GCSE, but we'll cover it. So it's the force experienced by objects when they are placed into a fluid. So again, a liquid or a gas being a fluid. Now, that word fluid comes up again when we look at heat transfer, looking at convection, for example. Okay, an object will float on a liquid if the upthrust force equals its weight. The hot air balloon there, the situation you got there, it rises when the upthrust from the surrounding air is greater than the balloon's weight. Magnetic forces, now that's a whole topic in itself, really, okay, but later on. But between magnets, but also the force that allows electric motors to work, okay? Not sure if you've covered magnetism and electromagnetism by now, but I'm looking at this as a recap of the whole course. And then you've got electrostatic forces, okay? So attractive or repulsive forces due to bodies being charged up. So again, that's looking at the electricity topic then, which in our school we teach in year 10. Okay, there you go. You've got a Van de Graaff, a large Van de Graaff there. It's causing the girl's hair to rise because they're repelling each other, charges in the hair. Right then, now I promised in the last video that we'd look at vectors and scalars in more detail because we were looking at speed and velocity. So all physical quantities are described by a magnitude and a unit. Vectors also need to have a direction specified, okay? So magnitude is just size, okay? Examples then of vectors would be displacement, which is in lots of courses. It's not in the current course that I teach at XLI GCSE, but it is in most of the other GCSE courses, okay? Displacement, velocity, acceleration, and force. These all are vectors and need direction written down in an answer, okay? Whereas scalars, they don't have a direction, okay? So distance doesn't need a direction. Speed doesn't either, or mass, work, and energy doesn't make sense. Now, one thing that sometimes students do get struggling was, because I've said energy there, but that includes kinetic energy, okay? Kinetic energy is a scalar. Again, you don't have to, you don't look at direction when you're looking at energy, okay? Temperature sometimes comes up as well as being a scalar as well, but I think that includes all of them there, really, okay? When you represent vectors, we use arrows with a straight line. So looking at displacement there, 50 meters east. In that particular example, the arrow indicates the direction and the length of the line is proportional to the magnitude, okay? We need to have some other displacement there really to compare it with, but we're saying there that, you know, that length of that line is proportional to the size 50, okay? Then we're looking there at displacement 25 meters at a 45-degree northeast angle there, okay? So addition of vectors is important, okay, in terms of direction. So the original vectors are called component vectors, and these are all weights here, okay? Well, sorry, forces, sorry. So you've got, in the first object there, you've got 4 newtons pulling in one direction, and then you've got 6 newtons pulling in the same direction, okay? So obviously it's important to specify that, you know, because otherwise it could have been 6 going in then 180-degree direction, or could be going any other direction, to be honest, okay? It would be a much more complicated question. But they're both going in the same direction there, okay? So you can add them up. And so the resultant, that's the important word for today, the resultant force is 10, 4 plus 6 newtons, okay? So the final overall vector is called the resultant force, or the resultant vector, okay? Now, when they're in opposite directions like that, you get a different answer, okay? Obviously, because they're in opposite directions, not in the same direction. So here you've got 6 take away 4, okay? And you can see again that the size of the 6 line and the size of the 4, you know, they're proportional to their numbers, okay? And hence the resultant of 2 is going to be equal to, you know, is going to be, the length of the arrow is going to be proportional to the size 2, okay? So the resultant is 2, 6 take away 4. Right then, let's have a look at some questions now in a minute. So a number of forces acting on a body could be replaced, but yeah, you could have loads of forces acting on a body. It could be replaced by one single force that's got the same effect as all the other forces acting individually, or acting all together, I should say. So that's called the resultant force. So if you've got 3 and 2 going in the same direction, then you can replace that with 5. Simple enough, I think. So if you'd like to have a go at the next one, pause the video and have a little go. So in case number 1, they both go in the same direction, 6 and 4, so simple enough. Can replace that with 10 newtons. Then you've got 4 newtons going 1 to the right and then 3 to the left, so 4 take away 3 will be 1 newton to the right, okay? Then in the other part 3, or question 3, you've got 7 take away 3 is 4 downwards, 6 take away 2 is 4 upwards, and then 4 take away 4 is going to be 0 newtons, okay? So no resultant force in that case. Now let's have a look at the effect of the resultant force on objects. Okay, so It's a bit weird the way that's come up. The resultant force, if there's zero resultant force, like on the previous example at the end, then the object either stays stationary or it continues moving in a straight line at constant speed, okay? That bit is a bit harder to understand, I think, because in the world around us, if there's no resultant force acting on an object, say if you flick a pen across a table, then as soon as it's left your hand, it slows down, okay, because of friction. So things like friction and drag, they mean that we're not really that au fait, as they say, with that first bit, right? That an object would continue moving in a straight line at constant speed. So if you're in space and you threw something in space from from the space station, then that would just go at constant speed forever, okay, until it hits something else, because there's no friction or very little friction in space, okay. If the resultant force is in the direction that the object was already moving, then it will accelerate, and critically, if in the opposite direction to which the object's moving, that force, then it would decelerate, okay. So this is sort of leading up to Newton's first law, okay, which is an object remains stationary or continues moving in a straight line at constant speed unless acted on by a resultant force. Okay. Now, some courses require you to state Newton's first law, but a lot of them don't. It tends to be Newton's third law that they want you to sort of write down sometimes. Okay, but check on your particular course. Okay. But this is really what this is talking about here. Okay, and the hardest bit is when there's zero resultant force. Was it already moving before? If it wasn't, then it stays stationary. If it was moving, then it continues moving at constant speed, okay? So 2 examples here. So you've got a man pushing a box there. The box will move when the man's push force is greater than the friction force. And then you've got a plane example. The plane will accelerate it provided that the engine force is greater than the drag force. So simple examples there. Example 3 and 4. The brakes exert a resultant force in the opposite direction to that car's motion, causing the car to decelerate. Hopefully before it gets to the lights there, okay? Then you've got a linear air track there, and you've got, once released, the glider moves at near constant velocity as it experiences nearly zero horizontal resultant force. It's not perfect. I mean, the rider will eventually slow down, okay? But it's a pretty good example. The only other time you might see that in your life is when you go to fun fair or somewhere that's got an air hockey table, because that lowers the friction's pretty low with an air hockey table as well. Okay. Now, forces can change the shape, we said earlier. So a stretching force puts something under tension. Okay, so it's a tensile force. And then you could get compressive forces, which squish an object, basically, compress it. Okay, squashing force. You can have brittle materials then, like glass. They don't change shape easily, and they break before any noticeable stretching occurs. And a less common term, really, resilient materials don't break easily. Not something that comes up in most courses. Now, something that does come up in pretty much every course is elastic materials. Now, elastic materials, they return to their original shape when the forces on them are removed, okay? Plastic materials, then, on the other hand, they retain their new shape, okay? So the word plastic we use to describe lots of things in the world around us, okay? But in a physics definition, that's what it means, okay? Something's plastic if it retains its new shape once the forces are removed, okay? And we're going to move on now to Hooke's law and stretching springs, which is related to this, okay? So hopefully you've done this experiment already in school, where you take a retort stand and you put a spring on there, and with some adding masses to a spring and measuring the extension, okay? Now, you don't want to put too much in terms of masses on there or weights, because it might permanently stretch springs, okay, which is not really what you want to do in this experiment, okay? And here's some data on adding masses to the spring, helical spring. Now, if you plot a graph of the force, now I was talking about mass there, but you can convert the mass to weight. Weight is a force. Then you can plot a graph then of force against extension. Couldn't be in meters, mine extension in this particular case, you've done centimeters. And it should be a straight line going through the origin, okay, for a spring. Not for every object, okay, but for a spring, force is proportional to extension. So that relationship there is called directly proportional. It's through the origin. But now one thing I want to make clear here, the words or the terms proportional and directly proportional are exactly the same thing, okay? A straight line through the origin like that is proportional and directly proportional. It's a bit of a thing over the years that people have learned it in an incorrect way, that they mean two different things, okay? I think the confusion arises where if you see something called a linear graph, where it'll be a straight line that doesn't go through the origin, that isn't proportional, okay? Proportional or directly proportional means going through the origin, okay? A straight line. And that also means it obeys something called Hooke's law. So Hooke's law states that the extension of a spring is proportional to the force used to stretch it. Oh, another thing I wanted to state here was, I don't know if you remember when you've done this experiment before, if you're using this as a form of revision, that this graph's a little bit odd here, and it doesn't really matter which way around you use the variables here. I think really you should plot extension on the y if you're going to follow the variable rule, okay, and plotting the force on the x. But there's a reason, certainly at A-level physics, why you plot force on the y, okay? But really, in most courses at GCSE, it's not important, the orientation of the axes. And so if you did an extension on the y and force on the x, that's fine, and it would go through the origin again, okay? Yeah, so Hooke's law states that the extension of a spring is proportional to the force used to stretch it. Now, often when you do this experiment, go back to that graph again, if you might not actually get a straight line through the origin, you might actually get it going not through the origin. It would be a straight line, but what they call a linear graph, not quite going through the origin. That's because of a systematic error in measuring the extension, okay, depending on how you've measured it. So proportional means that if the force is doubled, so is the extension. And so as it, just to go through that again, the line of a graph of force against extension will be straight and go through the origin for a spring, unless it's gone beyond something called the elastic limit, okay? So let's have a little look at the actual sort of maths of this. So spring of original length before you stretch it, 150 millimeters, extended by 30 millimeters by a force of 4 newtons. Calculate the length of the spring if a force of 12 newtons is applied. Okay, so if you want to have a go at this, pause the video. Right, so first of all, let's look at that first case then. Okay, it's extended by 30 when 4 newtons is applied. So 12 newtons is 3 times 4 newtons, okay? And as we said on the previous slide, that any new extension will be 3 times the extension that was produced by 4 newtons. So 3 lots of 30 millimeters is going to be 90 millimeters, okay? So that isn't the answer, though, okay? And this is another sort of pitfall, an exam technique thing. It asks you for the length, or the new length, they often say, right, of a spring if 12 is applied. So it's, whilst it extends by 90 millimeters, it was originally 150 millimeters long, okay? So you have to add that on, so that the final answer is 240 millimeters if you're going to use those units, okay? So there's a few things you could fall into the trap there, okay? Now, the elastic limit I hinted at earlier, so up to a certain extension, if the force is removed, the spring will return to its original length, and as I said earlier, that is what an elastic material would be, okay? It's behaving elastically. If this critical extension is exceeded, known as the elastic limit, the spring will be permanently stretched, okay? Which isn't good if you want to reuse the kit. Hooke's law is no longer obeyed once you've gone beyond the elastic limit, okay? And so it won't be, a nice straight diagonal line. So the spring on the right-hand side has been stretched beyond this elastic limit there, sadly, so it's been permanently stretched. So that's what it would look like. If the elastic limit is exceeded, it will deviate from being a straight line there, okay? Sometimes you might have to label where the elastic limit is, okay? So it's where it starts not being straight, okay? Now, an elastic band, this is sometimes a tricky one. An elastic band, you just need to remember, really, I'd say, that it doesn't obey Hooke's law, okay? It's not a straight line. I mean, the thing is here, though, it really doesn't look like a straight line here. But if you actually do the experiment, it kind of does look a little vaguely straight if you've just got plotted points on there, okay? Certainly if you haven't got many at the start or the end. So you've got to be careful here. Just one of those things you have to remember, that it definitely doesn't obey Hooke's law. Because some exam questions can be a bit tricky, and students end up doing a straight line through the points where it shouldn't be a straight line, and they're missing out on marks. Okay. And that's the end of that one. Okay, so yeah, elastic bands, they don't obey Hooke's law. So there's been quite a few key terms in this video that you have to go through and check you understand, terms like elastic, brittle, and things like that. Okay, but I hope you enjoy that one. And if you have, please like and subscribe and watch more of these GCSE revision videos. Take care.